Okay, let's compute the volume of a solid revolution by using washers. So the reason we say washers instead of disks is because every one of these little slices has a hole in the middle. So there's a slice, and there's an inner cutout, a hollow space in here. So my washer is located at a y coordinate that I'll just call y. So that's its y position. And the thickness of it is dy. So that means I'm going to end up integrating in y by the end of this. I need to get a volume for that washer. And it turns out to be a little tricky. So I'm going to view it from overhead. There's the inner circle and the outer circle. I'm going to try to figure out the inner radius and outer radius so I can get the area of that and then multiply by the thickness. So when I look at my outer radius, so that's the distance from here to here, it's going to require me to invert this tangent function. So I have some location x here, that's my radius. And I've got to find out what is that x corresponding to this y on the curve of the tangent function. In other words, I have to solve this thing for x, and I get x equals the angle whose tangent, or inverse tangent, y. So that's my outer radius. Then my inner radius is a little bit easier, but requires the same inverting idea. I need the x corresponding to this y on the graph of y equals 2x. So I solve that really quickly for x, and I get y over 2 for that. So my outer radius is inverse tangent y, and my inner radius is y over 2. So to get the area of this thing, I take the larger area, the area of the larger circle, pi times the inverse tangent of y squared minus the area of the inner circle, pi times that radius squared. But you might want to clean up just a little bit. I could factor out a pi times inverse tangent y squared minus y squared over 4. So that's the area of this washer located at a height of y. Then I can write down my volume element, how much volume is in that washer. That's dV is equal to the area multiplied by the thickness dy. So there's one more challenge to the setup here, and it's that we have to find, so we're going to add up all these washers all the way from the tiny ones down here by y equals 0 all the way up to the final one up here at the top. But I have to find the intersection of these two curves in order to figure out what that y value is. So to get this done, I'm going to have to use some kind of technology because there's no analytical solution to this equation. And what I'm going to do here is use wxMaxima, and in Maxima you have to express it this way, so these two are completely equivalent equations, but Maxima's approximation algorithm is made to find out where something is equal to 0. So it's not meant to do this approximation directly, it's meant to do this one. Alright, so let's toggle the Maxima real quick. And I'm going to use the find root function for this. So I go find root, tangent of x minus 2x. And then I have to give an interval to look on here. And be careful about this because the tangent function is periodic. Has a period of pi and repeats forever in both directions. So there's going to be a lot of intersections of these two functions, but we're interested in this one that's just slightly bigger than 1. So give Maxima a pretty accurate interval to work with. I'm going to look for a root between 1 and 1.5. And when I do that, I get 1.166 if I round it. But really what I want there is the y intersections, so I could just plug in x to the easy equation here. Y is 2x, so all I have to do is multiply that previous result by 2. I'll just do it in Maxima just because I have it open. Percent just means the previous output, so I said take that thing and multiply it by 2, and I get 2.331. All right, so that's going to be the end of my integration interval as I add up all these washers. So then I get into my integral. Now that I have dv phrased entirely in terms of one variable y, I can use an integral to add up the dv's. And I'm going to go all the way from y equals 0 to y equals 2.331. My integrand is pi inverse tangent y all squared minus y squared over 4 dy. And I don't know about you, but I don't know how to integrate a square of an inverse tangent function, so I'm going back to the computer algebra system for this. So I have pi inverse tangent squared y. Okay. So I'm going to try the integrate function, but this only works if there's an actual analytical solution to the problem, and I doubt that there is, but I'm going to just check because I'm curious. So I have pi, that's percent pi in Maxima, times inverse tangent, that's a tan in Maxima, inverse tangent of y all squared minus y squared over 4, so that's 0.25 times y squared. I think I've got the integrand correct. I'll just check real quick. Okay. And then as y goes from 0 to 2.331. All right, so Maxima, it did a bunch of stuff with the decimals, but in the end, when it tried to do the integral, it couldn't. So it just spit out the same integral that we started with. This is Maxima's way of saying, I give up. So instead of the integrate function, we're going to use the quad QAG function. That does numerical approximations of integrals. And you have to specify which algorithm to use, choosing from between 1 and 6. And it doesn't matter for us which one we choose. I hit shift enter and I get an approximate volume of 1.787, so I'll call it 1.788. Let's see. Oh, here's my pen. Okay.